So we are learning about surface integrals, section 13.6. And really, a lot of the ideas that you're learning in chapter 13 are ideas that have applications in physics and engineering, for instance, and other sciences. Now, we suppose, I don't think you have any problems in the homework that relate to this, but I thought it would nevertheless be good just to mention it. Let's say that you had a thin sheet, some aluminum foil, and it has the shape of a surface S and a density mass per unit area at a point. So this is not a lamina in two-dimensional space. This is a surface in three-dimensional space. The mass would be equal to the double integral over, it would be the surface integral, where rho is the density function. And then the center of mass are these formulas here. So you have seen center of mass used now. You have seen it used in you have seen, I'm going to say it right. You found the center of mass for a lamina. You found the center of mass for a wire, okay, which would relate to a curve in space. And, center of mass for a three-dimensional object, okay? And now you can have a center of mass for a surface. And you can see the formulas, they're always similar in nature. But let's move on. Let's move on here. So, all right. Hold on here. Okay. Okay, so now what we want to do is we want to show how surface integrals are important to find what are called flux rates. Okay, flux is the rate in terms of mass per second that an object, that a liquid flows, well, if we are going with positive orientation, it would be flowing outward from the surface. If we're going with negative orientation, it would be flowing inward. So you see in figure 6, they have a normal vector to the surface going outward and a second normal vector, n sub 2, flowing inward. But they're directing us to figure 7. And these are two orientations for an orientable surface. So a surface, fluid could flow out from the surface from a source, or it could flow into the surface from a source. And when we compute these flux rates, we're assuming, let me see here, I want to make sure I have it right. We're assuming we're talking about outward orientation. That would be the left figure in figure 7. Now, let me see here. Let me one moment. So these normal unit vectors, okay, if you're, and this is just, I'm just thinking sort of maybe I'm trying to help you understand where applications could be. If you have a surface and fluids flowing through it, you want to know you want to know the flow rate, and in terms of these, how is the rate of flow when the fluid flows out from the surface in the direction of those normal vectors, okay, those normal vectors to the surface. Now, if you picture, like on the left figure, in figure 7, if you picture each point, and there's a little plane at each point, that's essentially equivalent to the surface if you have the plane small enough. Well, the normal vector we could represent this way, the normal unit vector. So remember, anytime on a surface you have two curves to the surface, one curve is where you hold one parameter constant. The other curve is generated when you hold the other parameter constant. When you take the cross product of those, of the derivative vectors for those curves, that's going to get you the normal vector to the point on the surface, because the derivative vectors are tangent to that point, and a tangent to the surface at that point. And if we want the normal vector to have unit length, just divide it by this cross product. Now this is going to come in handy. This is going to come in handy later on. But let's go now to, I want to go to, oh yeah, here, figure 8 is positive orientation. The flow is coming out from the surface. And figure 9 in section 13.6 is negative orientation. So that's flow coming in. So obviously flow rate going out, well, yeah. So, all right, now let's continue on here. Sometimes it's best to just say what needs to be said. For a closed surface, the convention is that the positive orientation is for one for which normal vectors point outward from the closed surface. And we just saw that in figures 8 and 9. Okay, now let's go here to surface integrals of vector fields. Surface integrals of vector fields. So suppose that our surface S is an oriented surface with a unit normal vector, and imagine a fluid. Okay, I'm just reading from the top here. Reading from the top. Okay, imagine a fluid with some density and velocity. Okay, so the density changes from point to point in the fluid, and the velocity changes from point to point, like current, you know, in the sea or something. Think of S as an imaginary surface that doesn't impede fluid flow, like a fishing net across a stream. Then the rate of flow in mass per unit time per unit area is equal to rho, the density, times the velocity vector. And it says if we divide the surface into small patches, we can approximate the mass of fluid per unit time crossing the surface at the patch, S sub ij, in the direction of the normal vector by this quantity here. Okay, so I want you to, you know, the unit for that quantity is mass of fluid per unit time. It's a rate. And I want you to feel comfortable why that is the way it is. So let me go to the whiteboard here. Okay, I want to try to do this efficiently. All right, so what they're saying here is that the dot product of rho with the velocity field vector, no, I'm sorry, let's say that again here. What they're saying is that density times the velocity field dotted with the normal vector times the area of the ijth patch. They're saying the units for that are mass per unit time, flux. And I want you to feel comfortable why that's true. So why is this? Well, first of all, let's look at rho times the velocity field. The units for rho are mass per volume. So density is mass divided by volume, right? And the units for velocity, now I'm talking units. The units for velocity, let's just say it's grams per second. Okay. I want to be careful here. Hold on. No, I want to do this in American units. This will be a little easier. I just got to help you get a feel for what they're talking about here. So volume, let's say, this is an example. Let's say volume is mass per cubic foot, and the velocity is in feet per second. So what's going to happen, of course, is that this here is going to become mass per feet squared times 1 over second. But we could write that as mass per second in terms of units. That could be thought of as mass per second, okay, divided by feet squared. So what you have here is mass per unit time per unit area. And that's what they mention that in when they talk about surface integrals of vector fields, they mention that the density times the velocity field is rate of flow, mass per unit of time per unit area. But we want to arrive here. Okay, we want to arrive here. So what we're going to do, okay, is now we're going to consider, here's our surface. And the velocity field is density times let's consider our force field to be density times the velocity field. Notice that's not at a right angle to the surface, right? But if we were to construct a normal unit vector to the surface, and when we talk about rate of flow coming out, permeating from a surface, we're interested in the flow as it's coming out perpendicular to the surface. But of course, depending on what your vector field is, it may not come out. It may not come out, but at a perpendicular angle, like you see in this picture. However, we note that if we take the normal vector and dot it with this vector density times velocity, okay, that's going to be, I mean, here's theta. This is going to be the portion of this vector field force going in the direction of that normal vector. And that's what we care about. That's what we care about. Okay. Maybe the strength of the surface depends on ultimately how the fluid, the rate of flow, comes out in a perpendicular direction. To me, that makes some sense. All right, so, but the dot product of the normal unit vector, remember, this is a unit normal vector, that n is. The dot product is equal to, I want to just hold on here. Well, yeah, I mean, why is this true? Why is this true? Because remember how the dot product is defined. It is equal to the product of the lengths of the two vectors times the cosine of the angle between them. But the normal vector, the length equals 1. So that's going to give you the length of that force field vector at your point x, y, z on the surface times the cosine of theta, right? Times the cosine of theta. Hold on here. So for instance, that might be maybe that is this vector here. Who knows exactly, right? I'm just sort of showing it to pictorially. Maybe that is the dot product. So, okay. Well, we know the units here. We know the units. I want to work with this. The units are, as you know, mass per second per feet squared. But let's say that you were to take this this dot product, and I mean, I guess technically it should be rho. I mean, I'm just going to write it as rho dot v times the normal vector. Okay, I want to be consistent with the book in their notation, but the interpretation is still the same, right? So let me put rho v here, dotted with the normal vector. We'll go in that order. Dot product, and let me make an adjustment down here. I'm just kind of messing up here. Hold on. It's going to take my time. There we go. And now we have, no, doggone it. All right, I know what I'm going to do. Hold on. Oh, come on now. Rho v dot n. And I'll note here that the units here, since rho v dot n, it's a component of the vector rho times v, and so the units are mass per second divided by feet squared in this little example, this here. Just like, taking the dot product of that vector with another vector, the units are the same, right? So, okay. All right. So let me just make sure we're doing good here. Right. Mass per second per feet squared. Okay, now let's say I took this and I multiplied it by the area of the ijth patch, capital S, ijth patch on the surface. Well, what are the units? You have mass per second per feet squared times area, which is feet squared. And so the units have to be mass per second. I mean, anything intuitively that helps you, that helps simplify this is good, right? You should know what you're doing here. And so every point on the surface, I can take a patch, and I can compute the density. Remember this density here, this density is allowed to be a function of x, y, and z. And the velocity field is also allowed to be a function of x, y, and z. So you don't have to have a constant density function. So, and you don't have to have a velocity, velocity field that had constant vectors. That wouldn't be any good, right? So, if we want to find the rate of flow across the entire surface, we could pick points along each surface, and at each point compute this quantity, density times velocity field dotted with the normal unit vector pointing outward from the surface, times the area of the surface. And now, what they're saying here in the book makes some sense. Yeah, this is the mass of fluid. Maybe I'll highlight it in pink. Yeah, this this density, this force field, which is density times the velocity field, dotted with the normal vector times the area of the patch at at that patch, we're at the ijth patch. That's the mass of fluid per unit time crossing the patch. So what if you wanted to get an idea of the total flux rate? Well, what would you do? What would you do? Well, let's take a look here. So let me just see here. So you could have a Riemann sum of that rho v dot n times the area. Take the limit as m and n go to infinity, and now you end up with a surface integral. You get a surface integral. See that? The double integral over the surface of density times velocity dotted with the normal vector d capital S. It's a surface integral. So surface integrals, you can use the formulas to compute surface integrals. And again, I like formula 2. Okay, but we need to somehow introduce, it would be helpful if we could replace the, we know, hold on here. Hold on. My dad was an expert in this. That was his field. So yeah, this is interpreted physically as the rate of flow through the surface. And in terms of a picture, I mean, I showed you a picture on the whiteout board, but you know, this is pictorially what's going on in Figure 10. And they say let density times velocity field equal your force field. So what we want to do, let me get this. I don't know why that is. Hold on here. We want to, I want to say this the right way. So if you let density times velocity equal the force field, then you'd have this double integral, this surface integral. And it says it occurs frequently in physics, even when the vector field is not density times velocity. And it's called the surface integral or flux integral of the vector field of F across S. So what we want to do is we want to do a few substitutions here to make this surface integral easy to compute. Well, the normal unit vector, okay, across any point on the surface, we already learned that normal unit vector, hold on. We already learned that normal unit vector can, oh, let me mention something else here. I better do it while I'm at it. So in this surface integral, you can write that in terms of notation, the flux integral is equal to the double integral over the surface of the vector F dotted with the change in this S vector. It's notation for flux. So whenever you see a double integral and then boldface F dot ds, D capital S and S is in boldface, that's a flux integral. But what we want to do is we want to make this a little easier to compute. So we remember that the normal unit vector can be replaced with the cross product of the derivative vectors divided by the length of the cross product of the derivative vectors because it's a unit vector. And then ds is equal to the cross product of the derivative vectors dA. Now, you know, where's that come from? Well, remember, hold on here, that I can probably put it up here. Kind of like to keep this here if I can. But I got to write smaller. Right, so delta S sub ij, the little area of the ijth patch, is equal to the cross product the length of the cross product of your derivative vectors with respect to u and v times delta u delta v. And you can think of that as delta A, right? As delta A. Hold on, it's trying to, delta A, piece of area. So then ds would equal the cross product, the length of the cross product, hold on. Really fascinating. It would equal the length of the cross product dA. It would. So we can replace that differential surface area, d capital S, with the cross product of the length of the cross product of RU with RV dA. Okay, and so, I mean, I don't know if in physics, if your professors go over formulas with you, but you can see here, you can see then, if you replace ds with the length of that cross product times dA, the lengths of the cross products are going to cancel out, and then that's going to give you a formula for flux. Oh, come on now. Okay, that'll give you a formula for flux, which is in the highlighted formula 9. How many think this is absolutely fascinating? I mean, I know it's a bit it's complex, but hopefully this discussion. How many found it helpful when I talked about the units to help when I show you why the units are what they are? Was that helpful? Okay, Narina found that helpful. Good. And Yeva, okay, good, good. It's always good to know, to have an intuitive feel why things are true. All right, let's look at an example. Let's go to an example now. So this is flux. This is our formula for flux rate. And here we go. So let's do this problem here. Let me give you a moment to copy this example down. Okay, so they're wanting us to find flux. And we remember that this stands for flux. We established that the flux can be found across the surface, can be found. I don't want it at 1 point. Come on, give me 3 or 2. The flux across a surface can be found by computing a double integral over some region D. Hold on here. Of the vector field F dotted. Hold on here. With the cross product of the derivative vectors, dA. So, of course, you have to find what R of U and V is. And in this problem, the surface actually, we're talking about a closed surface. and it consists of two surfaces, a sideways paraboloid along the y-axis, y equals x squared plus z squared, but we're restricting y to go from 0 to 1. And then the disk, x squared plus z squared less than or equal to 1 at y equals 1. So together, that's going to form our surface. Okay, but we're going to have to get the parameterizations of those surfaces. Okay, and it takes practice, and that's why this homework for section 13.6, you have to keep going strong here till like, you know, till your homework's done, because this is very important for the final exam. I haven't tested you on this material yet. You can be sure it's going to be prominent on the final exam. So, okay, let me just see here. I'm checking one thing here. Yeah. Okay, so I'm going to draw. So I'm going to draw the picture of the surface, which I have. Oh, by the way, this is a little table here of different formulas that I have made up. Would you like to have these formulas? I mean, even though you have access to the ebook, would you like to have this handout? Okay, Yavis says yes, yes, right away. All right. So I'll make that handout available under, you know, the handouts link in Blackboard. All right, Logan, no problem. No problem. Okay. So here's our surface. Our surface S consists of that sideways paraboloid along the y-axis unioned with the disk at y equals 1. Flux is computed with respect to out positive orientation. That means that the flow rate, I'm doing it with respect to vectors, the normal vectors to the surfaces pointing outward. And that's why I drew those normal vectors on the surface. So let me give you a moment to copy this down. The book has good examples too. I think with the book's examples and my examples, you know, you'll be in good shape for your homework. But it will take time. Do not wait till the last minute, okay, to work on it. All right, let me give you a moment to copy the picture down. If you have any questions, please ask. Okay, so one thing I want to comment on is our force field vector, our vector field, which is given by yi minus zk. this entire surface is located to the right of the XC plane. So the y vector, so the force field, you have a j component, which is the component equals y, and then you have a k component, which is negative z. So if you picture vectors emanating, like if you think about points, different points. Okay, in the surface, inside the surface, the vector field's defined at those points, and because the y is positive, don't do that. Because the y is positive, that means the vectors in the force field have to, since y is greater than 0 for this surface, any point inside the surface, or any point to the right of the XZ plane, and that's where our surface lives, any point, the force field, the vectors are going to the right because y is positive. And that means that the flow of this vector field is going outside. I want to say it the right way. Hold on. Now, hold on one moment. No, I want to be more careful about that. Just give me a moment. So this is a question here. I have a little question here, right? Do the vectors of F flow inward or outward from the surface? Okay, so there's a little question mark here. I want to say this the right way. And the answer is outward. No. God, I want to be careful here how I say this. I have to be very, very careful. Yeah, it would be inward. They flow inward. Because if you pick a point here where y is positive, so you're going to the vector, the vector in the vector field moves to the right, but it's also moving up because the z component is negative for like 0.1. So the vector field is flowing inward to the surface. But if you're above the xy plane, that's if you're below the xy plane on the surface 1. If you're at 0.2, okay, where z is greater than 0, 0.1, z was less than 0. There, because you have a negative z, okay, so your vector goes to the right but it goes downward because z is positive there. So these vectors, the vector field is not flowing outward with respect to the surface S1. And that means that the flux rate should be negative. Okay, the flux rate should be negative. It's like work. If work is not helping you move the particle, no, if the vector field's not helping you move the particle along a path in the vector field, if the net effect of the vector field is to hinder movement of the particle in a vector field, then work is negative. Well, same with flux. If the vector field if the flow is going inward from the surface, in this case it's going inward across surface S1, the flux rate has to be negative. So, all right, what we do is we have to parameterize this paraboloid. So instead of u and v, I hope you don't mind, I'm going to use x and z. Just let x be x, z be z, and y will equal x squared plus z squared. And every point here, I'm trying to draw points here, every point on surface S1, the x and z, x squared plus z squared would have to be less than or equal to 1, because the first surface hits that boundary circle at y equals 1, and there x squared plus z squared equals 1, right? So, we have to come up with a region D, and our region D is this circle, and inside the circle, right, with a radius 1. Are there any questions so far? All right, well, let's continue on. So now we get our derivative vectors, r sub x, r sub z, and we take the cross product. Now, the cross product, in this case, it matters the order in which you take the cross product. I decided to do the derivative vector r sub x crossed with the derivative vector r sub z in that order. And I got 2xi minus 1j plus 2zk. That order ensures outward orientation as opposed to rz cross rx. If you were to do the opposite, if you were to take a cross product the opposite way, you would get, instead of positive 2x, you get negative 2x. And instead of negative 1, you get positive 1. And instead of 2z, you get negative 2z. But I have to take the cross product correctly to ensure outward orientation. So remember, how was the normal vector defined? The normal vector was defined as the cross product of the vectors divided by the length of the cross product of those vectors. You get a normal unit vector. But we want normal unit vectors in terms of orientation, since this is the normal vectors are showing outward orientation. We want our normal vectors to point in the right way. And if the normal vectors, if we do this cross product in this order, the normal vectors will point in the right way. How can you tell? Based on the components here, right? The components are 2x, comma, negative 1, comma, 2z. How do you know that's the right orientation or the right order to do the cross product? Look at the components. In particular, I want you to focus on the component of j, which is negative 1. If normal vectors, if the direction is determined, the direction of the normal unit vectors is determined by the cross product. The cross product of those derivative vectors in that order, r sub x cross r sub z, you get a negative 1 in front of j. How do you know? Looking at the picture, okay, look at these normal vectors in the picture. Look at all these normal vectors. Look at them. Oh, come on, don't do that. Don't do that, please. Thank you. They go up, They go down, but they're always going in what direction? Those normal unit vectors for the first surface. They go up, they go down, but they're always going to the second component. So the first component of a vector determines forward and backward, right? The second component of a vector determines left and right movement. The third component of a vector determines up and down. All of these normal vectors here in the picture, are they pointing to the left or to the right? They're pointing to the left. Now, sometimes it's just a little bit to the left, but they're leaning towards the left. That means that you have to have a negative component for J. You can't have a positive component for J. You can't have a 1 because then the vectors would be leaning right. Okay, so you have to be a little bit careful with that. All right, let's continue on. Now we are ready to find the flux. So we have our flux integral, and we have our formula for the flux integral. And now it's just a matter of working it out. I'll let you copy this. For your reference, I put the vector field F here on the right and the parameterization of surface 1 on the right. And I hope everything is fairly clear. You would have to, of course, work this out. And you would use, it makes sense to use polar coordinates for this double integral. So, please work out. And you'll get negative pi. And that makes sense because we had said the flux rate should be negative across the first surface because of how our vector field here is defined, right? So, I mean, this is absolutely fascinating. We don't see too much of it in statistics, in mathematical statistics, but has anybody dealt with flux in maybe another class? Usually students haven't seen it yet. Okay, Yave has seen it. Physics, electric, and magnetic flux. Okay, there you go. There you go. All this relates to fields you're going into. Now I'm going to go back to the picture in a moment because now we got to get the flux across the second surface, that disk. But please let me know if you have any questions. Notice here, by the way, the circle is in the xz plane, right? So x would equal r cosine of theta, and y would equal r, no, not y, z would equal r sine of theta. See, so truly fascinating. And it's even more nice when you understand it from a basic principles. I'm just going to make that sine of theta a little better. Do they try in your physics classes to, you know, justify things a little bit? Or do they, I guess it varies from class to class, but here we try to justify our formulas from at least I do, from a fundamental sense. How many of you feel this course will help you with maybe one of your other classes? Or okay, Yeva's seeing that already. Okay. And Noreena's seeing that. Okay, good, good. Okay, well, let's go ahead here now. And so we got negative pi for the flux rate across the first surface. Now let me go back to the picture, look at the second surface. So the second surface, okay, which is this disk with radius 1 located at y equals 1. The normal vectors would point just directly to the right, and we already know, I want to say this the right way, that means that when we do the cross product, we have to do the cross product in an order such that the cross product of our derivative vectors has a positive component for the j vector. Okay, so that our flow is going outward. So okay, let's get the parameterization for that second surface. That's the disk at y equals 1. So y equals 1. I'm going to let x be x, z be z, and x squared plus z squared is less than or equal to 1, and that will give us that will trace out that, well, it'll give us the surface S2, that disk. And again, x is r cosine theta, and y is r sine theta. And if for this vector function of parameters x and z, if you did the cross product of rz cross rx, you would get a 1j, which is what you want. You want your flow, you want your normal vectors are pointing to the right. So you want your flow going to the right. What I mean is you want the normal vectors go to the right off of that surface S sub 2. And so when you do the cross product of those derivative vectors, you want to match that. And so you want a positive j component, which is 1. All right, so there's the j vector here. There's that j vector. And if we do f of r xz, we're going to get 0, 1, and negative z. Because there, I mean, this vector field is like 0i plus yj minus zk, right? So um, given your parameterization of this surface, well, x component is x, y component is 1, and z component is z. So we're good. Would the flow rate be positive or negative for this vector field across that second surface? If you think about the vector field here, the vectors are all, they're going up and down, okay, depending on whether you're below the xy plane or above the xy plane. But because the y coordinate is positive, where to the right of the xc plane, all the vector field will naturally, all the vectors will flow outward from that second surface, and so the flow rate should be positive. And when you work it out, you will get positive flux. And I'm not putting in all the steps in the notes because first of all, I know you know how to do them. I know you can do a double integral, and I want to save a little time here. But of course, on the final exam, you'll put in the work for your double integrals. Is this sort of jive for those of you that have seen flux? Is my treatment of flux jiving with what you've seen in your classes? Is it? It's a very I do it very basic, but I hope it helps. Let's put it that way. Okay, Yeva. Yeva says it's similar. She didn't recall doing double integrals. Well, probably because you haven't had calculus 3 yet. But now, you know, now you'll be okay. So, okay, if we want to get then the total flux across, remember, the surface S is the sum, the union of surface S1, which is the paraboloid, and surface S2, which is that disk. And so you just add the flux rates together. It makes sense. If you're trying to get the net rate flow, you would add up the rates across the different surfaces. And all this work, look at what we get. We get a net rate of 0. We get a net rate of 0, net flow rate. The flux equals 0. Are there any questions at all? Who's feeling reasonably good? Give me a thumbs up if you're reasonably good. I know you have to do practice, but But how many at least are initially? Wonderful. Lexi's reasonably comfortable. Yeva's reasonably. Norina's reasonably. Good. Good. Logan's reasonably. Okay, great. Great. Okay, well, what I'd like to do, I'm going to go ahead then. I'm going to stop the recording. Very good. We've completed now section 13.6, but I encourage you to look at their examples too in the book. Very good.